Hi. Now we will look into the chapter 10, the GIS Data Structure. So basically, when we talk about the data structure, something that we want to see now is the form of the data itself, either the characteristics and also the representations of the data and how does it looks like, and as well as how we represent the real world in the GIS vector. So the idea of the data structure, especially for the spatial data structure, is how we want to represent the real world, especially the data of the real world being represented in the GIS. And we know that there are two types of the data structure, which is raster and vector. What are raster, what are vector, what are the pros and cons between two types of those data, okay? And of course we want to see the accuracy of the data and how we want to ensure the accuracy of it with the topology. So when we talk about the concepts of vector and raster, as you see here, basically this is the real world, almost the real world that being represented. We have houses here, river, trees, and also land. So when we talk about raster representations, it is something like an image, a photos, where all of the attributes being represented in specific codes that is kept in the image pixels. So here, example here, this is the house and river. So it was represented here as several dots of the pixels as house, rivers. Yeah, we can see that it creates the combinations of the pixels in specific directions, and also specific shape represents the river looks like, tree, and others. So this is how raster being represented. When we zoom it, it becomes it was shown in the blockish representations. Okay. However, for the vector representations, most of it represents the real world either in forms of point, line, or polygon, according to the nature of the feature itself. So points could be the points of the houses, right? Polygon basically the cumulative of the trees to create an area. Line to best representing the continuous features such as river or roads and others. So basically when we talk about the area in the raster, so area in raster is covered by the grid with the equal size cells. So basically the pixels that form the raster data, it has a specific measurement or dimensions of the pixels based on the type of the data source, such as it could be from the images, or it could be from the aerial photography, or scanned images, or scanned maps. And location of each cell would be calculated from the origin of the grid. Basically the grid, the 0 point of the grid will be from the left side of the further down from the left side will be the origin of the grid, and those cells will often called the pixels. So the grid cells within the image raster, it was called pixels or picture elements, and the raster data often called as a image data. Even though some of the raster data is not an image data, especially when we come out with the land use data, thematic data, and so on, it was not an image, but how it was presented is an image data. But attributes are recorded by assigning each cells a single value based on the majority features. Therefore, in the raster data, for each cells or each block only can hold one single data, cannot keep more than that, and such as land use type. And for the raster data, it's very simple, it's very straightforward. It doesn't have any database, doesn't have any topology, and so on. So it's easy to do the overlays or analysis, where you can just combine and come up with the analysis, and something simple analysis and more. And it is a simple data structure where most of the informations are directly stored in each layer as a single table, and it doesn't keep variable which is in the long characters or long integers. It only keep in the codes, type of codes, in the simple integer. and computer database management was not required, right? And along the center, along the pixels, they have the latitude or longitude, or in the Cartesian coordinates, and those latitude or longitude will be kept in between, in the middle of the pixels, where the single values will be associated with each cells. It will not keep more than one value, and typically it holds 8 bits assigned to value. Therefore, there are 256 possible values. So of each value will represent specific information, and there are rules needed to assign value to cell if the object does not cover the entire cells. So what kinds of the rules basically is about, if the real world, when we transpose into the image pixels, we only if the features covers most of the pixels, therefore the pixel will be assigned to that particular features. Example here, if we talk about the land use, where the land use in the real world, when we try to put in the raster image, so the boundary is less than half of that particular pixel, therefore we will not consider it as a part of the, or it will not, the information will be not kept inside the pixel. So it must be the majority of the area, especially for the continuous coverage features, and the values that are kept are ordered at the center, the cell of center, and it must be touches the cell for the linear features, right, to represent the linear nature of the features, such as roads or rivers. And there are some weighting to ensure rare features are being represented, meaning to say that if the features are not important, it will be not represented, or it will not be visible in the raster data due to the limitations of the pixels to hold more than one value. Okay, example here. So basically, when we talk about the cell pixels or the values in the pixels, it only kept the values in the integer or in the numbers, right? We don't keep it in characters or in words. So this is the drawback of the raster, but due to this nature, it's easy for us to do some manipulation or analysis, because computer understands numbers as opposed to the characters, or as opposed to the words. Okay, so in terms of analysis, it's very easy. However, for the users to understand it is quite complicated. Therefore, there must be rules, there must be class, there must be classifications, there must be legends to understand it. And the derivation that you can do is either additional or subtractions of the values to create a new raster data, which is an output, or which is an result from the simple analysis. So it can be done in that way. And one of the sources of raster data is basically from the satellite data, such as Landsat or Spot. It could be some from the scan aerial photography, or come from the digital orthophotography from the airborne or from our drones. And also there are some from the scan maps, and also from the documents such as tables and reports and more. So when we talk about the raster representations, so this is taking the example that suppose in the real world we find a triangle shape like this, a very sharp triangle, and we want a raster to represent this triangle basically. So we choose a number to represent it, and triangles will be represented as 1, and non-triangle, the blue one, will be 0. So due to the nature of the raster, it has pixels, and pixels are in the block color, in the block shape type. Therefore, it tries itself, the computer will try to accommodate the shape of the triangle, okay, where most of the, you can see here, half or more than half of the image of the coverage in the triangle, okay, covers the triangle, okay, will be assigned as 1, which is this block will be assigned as 1. However, for the areas they are covered less than half, so it will consider as a non-triangle. Therefore, the shape will be something like this. So the higher the higher the resolutions of the pixels, okay, the better the representations of the area. However, when we try to zoom in, it still show you this kind of the block type of features. And we can see here that raster version of this triangle does not accurately represent the vector version of the triangle due to the nature of the pixel itself and also the raster data itself. Therefore, the accuracy of the data will be compromised a bit, okay, but it's not totally compromised. And in reality, the raster is simply an n times m array of the numbers where different numbers represent different spatial entities. So, for example, this triangle will be in nature will be like this, and in the computer it will be kept like this: 0, 0, and 1, 1, 1. This is how the computer understand it. So when we then provide a legend for the raster to make sure that we can understand it. So 0 is the background and 1 is a triangle. So from here, then you can understand that this is the triangle shape of the features, and the 0 class will be the background. Okay, so in the real world, if the features like this, the land use, when we put into the raster, it becomes something like this. Okay, and rest representation as the computer understand numbers, so it will be something like this. And in the database, we do have some lookup table, and it shows the numbers and also the value, okay, and the frequency of the each pixels. Okay, and these examples for the points, okay, the points that we collect as a cells, something like this. Line sequence of the cells become like this. You can see the continuity of the pixels trying to represent the shape of the line in the real world, or the area as a zone of cells, something like this. After we discuss about the raster data structure, now we look into the vector data structure. Different from the raster data structure, vector is more straightforward, simple, and is more flexible. So it has three types of data structure, which is point, line, and polygon. So points is basically is 0 dimension. It only have a single x and y coordinate, and there's no area. And most of the time, most of the data from the points is data that we captured from our GPS. And we have line, which is 1 dimension, where it is 2 or more connected x and y coordinates. So for every line, for every edges of the line, there are points basically, and it was being connected to each other, and it has direction. Example, rod or string. While polygon is a 2 dimension, where it is 4 or more ordered and connected x and y coordinates. It has its own sequence to come up with the polygon, and it must be the first and the last x and y pairs must be the same. So the first point will be the last point, and it must enclose an area. So example here will be the country, boundary, leg, and more. So a vector data model uses a point to store by the real Earth coordinates and requires a precise coordinate system. So when we talk about the precise coordinate system, it could be from the geographic coordinate systems, which is WGS 1984, latitude or longitude that we use from the GPS. It could be from the Cartesian coordinate system. It could be from the X and Y coordinate systems, the local projections, stat plan, UTM, universal transverse marker, and more. And lines and areas are built from the sequence of the points in order. Therefore, the idea of the basic vector, the basic form of the data vector will be the points. It's very important because we want to keep the coordinates and accordingly. And lines have a direction to the ordering of the points, and polygon built from the points and lines as well. But it must be enclosed. It must be close the area to create the area, the enclosed region. and vectors can store information about topology. So topology is basically about the mathematical process to ensure the accuracy of the shape, given that the changes of the projections, okay, where it might change the coordinates and the real locations, but it could still keep the actual shape of the boundary. So points, line, and polygon. So the idea will be single x and y coordinate pairs. Line is a series of x, y coordinate pairs, and polygon is an area as a closed loop for x, y coordinate pairs. So point, okay, it could be a single point of represent the house. It could be a linear phenomena where all of these rows buildings represent as a one single point of town. It could be the area phenomena where it could show you the point of the phenomena, and more. Line, however, line, it shows you the shape of the phenomena, the railroad, and many more. For area, we have a lot of points that we can conclude it in the polygon, or from river, the network of the river, we can conclude as a watershed, and many more. Right. So vector data is really relies on the precise coordinate system. So we have this geographic coordinate and Cartesian, and it's very important. So how about the raster and vector? We trying to compare each other. Raster data model, well, the location is referenced by a grid cell in the rectangular array. So when we talk about the location in the rectangle, it is based on the spatial resolutions of that particular grid cells. If it has a higher spatial resolution, so it is quite accurate. However, for the low resolutions, the accuracy will be questionable. When we talk about 1 pixel, is about 100 meter, so that accuracy is about 100 meter accuracy of that particular coordinate, so it can be questionable. However, for the vector data, the location reference is exactly by the x and y coordinates, okay, and it can be linked to form lines and polygons. Therefore, in terms of resolution, there is no resolution available because it really shows you the exact coordinates x and y on the real world. Therefore, in terms of accuracy of the coordinates, vector data is much more better. For the raster data model, we try to look into the attributes. So raster data model, the attributes is represented as a single value for the cell. Therefore, it requires us to have the legend of the class to identify, to explain about the values that being kept in the raster data grid. However, for the vector data model, the attributes reference through the unique ID, and it is come from the database management system. So you can put either numbers, words, paragraph to explain what is that particular point, and it can have a lot of the columns to explain it. Therefore, in terms of the attribute, it is more flexible, okay, and it can be updated. Okay, so raster data model is basically data came from the remote sensing images, scan maps, or evaluation. But for the vector data model, most of the time it can come from the existing data, or the user have to create it by their own. So raster data model, it best to represent the continuous features such as elevation, temperature, soil type, and land use. However, for the vector data model, it best to features representing the features with the discrete boundaries such as political boundaries, transportation line, and many more. Okay, so this is how we present it. Raster, this is the entities, and how we present either in the raster view or in the vector view. Okay, so these are the advantages and disadvantages of between the raster model and the vector model. So I want you guys to understand this, and we will discuss more in our discussion later. So hopefully that we can discuss on this and what are the best data to be used, either raster data or vector data, and according to application, we will discuss it later. Okay, and to compare between the raster and vector, okay, so we will discuss it more in our discussion as well, so please read it and try to look into the internet, and I will ask you some questions about this. Okay, so we talk about the raster data. They are better when it is for the boundaries are gradual, the features are along the continuous surface, or to combine a lot of data layers quickly and cheaply, easy analysis, easy representations, and just come up with that, or to use the remote sensing data, and also to do some prediction, modeling and simulation. So this is where the raster data are being used. So can you tell me what kind of application that uses a raster data? Maybe we can discuss it. Okay, I want you guys to give examples of what kind of raster data that you use in your job. However, for the vector data, it is better when to show the boundaries, they are abrupt of connections, looking to the relationship along the network, such as rods or streams, or you want to store many attributes for the spatial queries, and also to have a precise and high quality maps. And now we will look into the topology. So what's basically is topology? And topology can be defined as a property that describes the adjacency and the connectivity of the features. So the topology only can be used for the vector data structure. For raster data structure, there's no need for the topology. Okay, and what is topology? Basically, it is a mathematical procedures to define the spatial relationship, where it expresses different types of the spatial relationship, such as an area is defined by the lines comprising its border, and the line is defined by the points that compose its endpoints. Meaning to say here, all of those taking to example the polygon, it only can be defined as a polygon when all of the dots are connected together and encloses the area. If there is one point that is not connected to another point, or they have some leak of the boundary, for the topology, it will not consider it as a polygon. It will determine where are the errors and ask the users to do the correction. For the line as well, if there is unconnected line, even slightly small area, so it will not consider as a same line. So topology basically trying to check the validity of the relationship of those features. Therefore, it really helps to ensure the quality of the data before the data can be used for the further analysis, right? And it logically determines exactly how and where points and lines are connected on a map by means of the nodes. So in topology, it really describes the spatial relationship in terms of the connectivity between lines in the network. Either those lines are connected to each other, okay? For the contiguity or the adjacency of the polygons, either those polygons are really next to each other, or there are some gray areas or no man's land area in between, or the containment. So this refers to what is within a polygon. Okay, so basically, are those polygon within the polygon, is within the polygon, or is on top of that particular polygon? Something have to be checked. The proximity as well, how near it is, and the direction of the line. Either directions is the same directions, is parallel, or it is not the same directions from one point to another point, it collides each other or not. Why we want to check this? Because in order to represent the real phenomena of the real world, we try as much as possible not to have this kind of bloopers, this kind of errors, as it will affect the analysis that we want to conduct. And of course, when we talk about the, let's say we talk about the rod network, if the rod network is being falsely or wrongly assign the directions, and it is collided like this. Okay, it was collided like this. So when computer trying to represent or trying to do the simulation, it assumes that those lines will collide each other. So all of the cars will be collide each other. So it will not give you a good result of the simulation. That's why we do have this topology. And what is important is a loss for the spatial analysis is very important. It's very important for the network analysis. It is convenient and efficient way of storing informations, because we don't want to have redundant data. We don't want to have this rubbish data. And the processing is much quicker when the small amounts of data stored, because we don't want to have the redundant data and so on. So we want to ensure that the processing is will be more efficient. Okay. So for the composite features, it refers to the spatial features that are better represented as a composites of points, line and polygon. So in ArcGIS we have these composite features where it creates one features which called as a TIN or triangulated area networks, where it is best to represent the surface, where it mimics the actual surface of the real world. Okay, and it keeps it all of this. It is derived from the points that we collected, the mesh points, which is elevation of the points of the elevation of the area, and we trying to make it into a 3D, something like this. Okay, so what's the advantage of using TIN? Okay, over the grid. The grid is basically raster data. The advantage is TIN is they have the ability to describe the surface at a different level of resolution. We can zoom in and zoom out. However, grid cannot do that because it is restricted. It is bounded by the cell or by the pixel resolution, and it is quite efficient in storing data. However, for the grid, it's very big. However, for the grid as well, it is easy to store and manipulate as is. It uses raster data. Very easy to integration and more natural appearance, as it shows you the continuous value. However, the disadvantage, for the TIN, it requires a visual inspection and manual control of the network, especially when the points is quite sparsely distributed. Therefore, the generated TIN will be quite questionable of the quality. However, for the grid, the disadvantage is the inability to use the various grid size to reflect areas of the different complexity of the relief. Okay, and from the TIN we can derive a grid data, which is a digital elevation model, and where it's a sample array of elevations that are regularly spaced interval. Okay, and the surface grid consider each sample as a square cell, which is a constant surface value, something like this. So in our practical later, we will try to come up with this kind of data, and also we will do some simple modeling. I hope that later in the lab video later, you guys can try and you guys can come up with the result that results of this kind of data. Okay, so what are the advantages of the digital image model or DEM? Advantage is a simple conceptual model, data cheap to obtain, is easy to relate to the raster data, and irregular space of point can be converted to the regular space by interpolation in the raster data. And disadvantage, it does not confirm variability of the terrain, and the linear features are nowhere represented because of the nature of the data is having a pixel or grid cell of data. Thank you very much.